Team SharpShooter. My name is Karina, and I'm joined today by Paul, Miltos, Bennett, and Jake to talk to you about our novel portable reactive camera stabilizer. Photographers require long shutter speeds for a variety of situations. This includes street photography, where artistic motion blur but a crisp background is required, nature photography, where both high dynamic range and high depth of field need to be achieved, and low light situations. However, long shutter speeds have their downside, this being blurriness, due to the user's hand shaking during the exposure. However, with SharpShooter, you can use the same settings but achieve a much crisper result. Keep in mind the shutter speed of 1.3 seconds is 40 times longer than the recommended shutter speed for this handheld photo. Current solutions on the market to stabilize cameras include tripods, which are highly stable but take time to set up and are cumbersome to move around. Gimbals, which take even longer to set up and also don't allow for natural interfacing with the camera. In-body and optical stabilization, which are seamless as they are built into the lens and body. However, these are less stable due to their displacement. This leaves a hole in the market that SharpShooter fills as a highly portable and competitively stable solution. It is ergonomic, quick to set up, and supports long exposures. We talked to stakeholders in both surveys as well as in-depth interviews to determine what they needed from us. SharpShooter needs to be small, light, last as long as a typical DSLR camera, be competitively priced, and last as long as the 2 seconds, covering the vast majority of shooting scenarios. Our design goal is to take crisp images. In order to quantify this, we use the S3 sharpness metric, which literature says closely correlates to human perceptions of sharpness. In addition, we found through our own data that the standard deviation of movement of a camera corresponds to this S3 sharpness metric, meaning that if we can reduce the motion of a camera, we will have crisper images. To further understand this disturbance, we attached a laser to the camera and tracked its movement. We found 2 important results that were further backed up by research. First, that rotational effects dominate those of translation, and secondly, this happens in the 2 to 15 hertz range, which is quite fast. So, given a rapid and random disturbance, if we can quickly and accurately apply an equal and opposite correction, we will have a stabilized image. To apply this correction, we considered a variety of solutions. First, we looked at passive damping, in which inertia as well as springs reject motions applied to the camera body. However, found this is not reactive and therefore not quick enough for our needs. Next, we looked at optical stabilization and improving it, but found it had fundamental displacement limits. Next, a kinematic chain in which the camera body moves relative to the user's hand. However, this inherently does not allow for ergonomic shooting, meaning it's not good enough for us. So rather than improving upon existing camera technologies, we had a radical idea. What if instead we use technology used to point satellites in the sky? Reaction wheels do just this, by applying corrective torques to satellites in order to stabilize them. We thought if we could miniaturize the system, it could apply those corrective torques instead to the user's hands, stabilizing images. It is reactive, has high displacement, supports high displacement, and allows for ergonomic shooting. To talk more about how we turn this crazy idea into reality is Jake.
Thanks, Karina. To take our idea from concept to product, we first developed a single-axis prototype to test our torque actuation methodology. We then moved to a 3-axis testbed to verify our sensing and control schemes. Finally, we developed a well-packaged user device. A reaction wheel consists of a flywheel to absorb the momentum introduced by disturbances, and a motor to apply a torque between the flywheel and the body. During an exposure, we must apply an extremely precise torque to stabilize the camera. To do this, we modeled the relationship between motor velocity, applied voltage, and resulting torque. We tested many different fitting methodologies, but ultimately developed our own piecewise surface optimization tool. Our model accurately captures the behavior in all regions while remaining computationally efficient enough to run at 600 hertz on a microcontroller. We designed a device that is not only effective, but also compact. To do this, we determined the maximum allowable flywheel radius as well as thickness, as well as the minimum inertia necessary to stabilize the device during an exposure. Within this feasible region, we selected the flywheel with the minimum mass to ensure user comfort. We are spinning flywheels at up to 20,000 RPM. At these velocities, even the slightest imbalance of the flywheel will result in vibration, ruining the photo. To prevent this, We are able to measure these vibrations using our device's built-in gyroscope and iteratively remove material from the edge of the flywheel at the correct location to reduce our imbalance by over 2 orders of magnitude. During an exposure, we need to accurately measure the relative orientation of the camera down to 1/100th of a degree, while using small, low-cost sensors like those found in smartphones. To do this, naively integrating the gyroscope would result in drift due to unknown biases. However, we're able to measure these biases online while the user uses the device by comparing the motion observed by the gyroscope to that observed by the accelerometer and magnetometer. In this way, our estimates converge rapidly to the true values, and we have highly accurate estimation. We model the dynamics of the system, detect disturbances using our sensors, and implement a PD controller to compute a desired stabilizing torque. We selected a PD controller over a controller with integral compensation because the disturbances to our system vary rapidly and unpredictably. We tackled many other design problems to produce a compact and effective system. We designed and built a custom printed circuit board to house our electronics functionality and interfaces. We sized a battery based on our current draw and endurance requirements. And we performed finite element analysis to verify that high power dissipation in a small device would not result in overheating. To talk more about turning SharpShooter into a consumer product, here's Bennett.
Thanks, Jake. So integrating user feedback, we iteratively designed our prototype for both assembly and ergonomics. We arrived at a 3-piece shell that fits snugly around our core technology. SharpShooter deploys in 3 quick steps. Simply screw it into the universal mount on the bottom of any camera, plug in the flash interface, turn the device on, and you're ready to go. The flash interface automatically detects when a user takes a photo, and the device begins applying stabilizing torques to the user's hands, but only for the duration of the exposure. When not in use, SharpShooter fits into any standard size camera bag or remains conveniently underneath the camera, ready for your next shot. So what can SharpShooter do? SharpShooter supports long exposure photography. So in this photo, this is exemplified by a crisp foreground and background, as well as artistically blurred photo subjects. But where SharpShooter really shines, though, is in low-light photography. This 1.3-second exposure is blurry and unusable. But with SharpShooter, that same photo is crisp. Here we see another example of a 1.3-second exposure. And again, the difference is clear. 1.3 seconds is, again, 65 times the recommended shutter speed for handheld photography. We also characterize the motion of the camera during the length of the exposure. You can see with SharpShooter off and with SharpShooter on, the motion of the user's hands vary wildly when the device is off. But with SharpShooter on, that same motion is highly attenuated. To see this in action, I'm going to hand it off to Paul for a live demo.
Thank you, Bennett. Judge Robert has agreed to be part of SharpShooter's live demo this morning. During this demo, he will take 1 second long exposures with both SharpShooter off and SharpShooter on. In the screen, we will see a live data stream of the motion taken by the judge's hands during this exposure. Judge, I want you to take a camera. This is going to hold the camera comfortably and try to keep it as steady as you can. This is going to be the handheld shot.
Okay, I need the focus?
Nope, just click the shutter. Thank you, Judge. On the left hand of the screen, we can see the trajectory taken by the judge's hands during this 1 second exposure. Now let's turn on SharpShooter and see how it compares. Turn the system on, take the same picture. I recommend you hold the camera loosely and don't put it next to your face. Let it do the work. Okay, that was pretty good. We normally find that it takes about up to 5 shots for you to learn how to master SharpShooter.
Yeah,
let's try that again.
There was a little kick.
Yes, don't fight it.
Also, keep your hands on the body of the camera instead of the device, and that'll improve your results.
The device is on there.
Is it on?
Yes. There you go. Thank you, Judge. If we look at the screen, we can see there's a great difference in the movement of the judge's hands during this exposure. Thank you, Judge. You may take a seat.
Thank you.
I will now hand it back to Miltos, who will finish the presentation.
Thanks, Paul, for that great demo. Now that we have proved that the SharpShooter can be used to indeed attenuate the motion of the user's hands, you might ask yourselves, how do pictures taken with SharpShooter compare to pictures taken with other stabilization technologies? To answer that question, we analyzed a data set of more than 100 pictures. And we actually proved that pictures taken with SharpShooter are far superior in terms of sharpness to those taken with its market competitors. But we also asked ourselves, what do real photographers have to say about SharpShooter? To answer that question, we put our device in the hands of photographers and asked them to use it in the field. Here's some of the stuff they said. Then for nature photography, where you have to bring around a tripod if you want to do anything above a 60th of a second, this would be amazing. Peter Michael, another professional photographer, said that if I'm taking 10 photos and it takes me about 5 minutes to set up each one, you're saving me 40 minutes. This is unreal. Finally, a professional photographer and filmmaker, Ted Knighton, put it simply, this is brilliant. SharpShooter is a consumer device, and as such, we are planning on selling it to the market. We have already filed a provisional patent for it, and we have carried out an extensive analysis to determine the manufacturing cost of producing it at volume. We believe we can sell SharpShooter for a very competitive market price of $300. With SharpShooter, we were able to either hit or exceed most of our metrics: the size, weight, endurance, and price. And we came just short of being able to support a 2-second exposure. However, moving forward, using precision motor bearings, we'll be able to support twice as long shutter speeds. By moving from a 3 to a 2-wheel system, we believe our analysis indicates that we can reduce the weight of SharpShooter by 25% with no sacrifices in terms of stabilization ability. Finally, by using an industrial-grade gyro, we'll be able to reduce the drift of our sensors by 70%, further improving the performance of our device. At this point, I'd like to acknowledge everyone that helped bring SharpShooter into focus, and especially Dr. Bruce Kottman and Dr. Graham Obasevsky. I'd now like to open it up to any questions you might have.
So it seems like the cost of the wheels, is there any possibility of going from a machine part to a cast part?
So right now, if we go to miscellaneous, and then to the cost model, right now, the reason why our wheels were currently made out of brass is that this was the most easily machinable material that we could use in the shop. What we were thinking was definitely moving from brass wheels to stainless steel wheels that would have an equivalent density and would give the inertia that we needed at the same size. And yes, for those kind of wheels, we could definitely move to a cast part and then do the balancing in a more efficient manner.
But to answer your question, the reason it's machined is because that's the most precise way to manufacture these wheels, and any imbalance, again, will just make the photo worse, not better.
How does it work at slower shutter speeds, right? So if I'm thinking about just everyday photography with children indoors and so forth, it's not usually a 1-second exposure. You know, maybe it's still a half a second, but you still get blur when the kids are looking. So is there a trade-off where because it takes a little time for them to spool up, or how does it work?
Absolutely. So, the standard, just to sort of give some context, the sort of standard rule of thumb is that 1 over the focal length of your lens is the highest you can shoot handheld, which is about 1 over 30 typically for sort of average lens. And so as soon as you get beyond that, we'll start to offer a benefit. But I see that you may not want to carry around this device for a very small benefit because basically when you start at that point, there'll be a small difference, and then the difference between your performance handheld and SharpShooter will get bigger and bigger as you go higher. But as soon as you get to 0.1 seconds, 0.2 seconds, the difference is definitely noticeable.
And in addition, you mentioned spinning up the wheels. The device does not need to spin up to a certain speed in order to function. It's not a gyroscope. Instead, it's applying stabilizing torques, and these torques happen at any velocity. And our graph that we had earlier of essentially relating a velocity to a given voltage to get a certain torque is very crucial.
Yeah, two-part question. One, how does this compare to photo image post-processing? With a lot of DLSSRs, and even your cell phone takes 10 pictures, optimizes, and software does it for you, right?
Right.
So, and you don't have to carry the extra 2 pounds on the camera, right? So I'm wondering if this, I would think this is an actual picture better. Second question is, you thought about applying this to something else, like people whose handshake when they want to paint, or I don't know. I would think that would be a great application because it's not for a 30-second exposure, have to do for a long time.
Right. So, sorry, the first part was.
How does it compare to camera image post-processing?
Oh, right. So there's definitely a ton of progress that has been made in post-processing, like stacking images and things like that let you get a lot more out of, especially lower-cost cameras. But there's sort of still this demonstrated need for supporting longer exposures because people are investing in cameras that have built-in stabilization technologies, and it's sort of like it's more of a complement than a replacement in that like the longer shutter speed you're able to use, you sort of inherently are able to vary the other settings to get an equivalent exposure that suits your needs better, especially in low light scenarios where because of the noise involved, you want to get everything you can out of your sensor, and I think this could be paired with digital post-processing to sort of maximize the benefit in both regards. Sorry, what was your second question?
Other applications.
Oh, right. So actually, one of the things we experienced with demoing was demoing to an older gentleman who was worried that his hands would be too shaky to take a picture, and actually, our device performed even better for him than it was for other people. So I think like you're absolutely right that as sort of an assistive device, there's definitely opportunities there, even within photography. If for people who feel like they can't hold their camera steady, on their own in the first place.
That's how we got. Thank you.
Thank you.